Welcome to this explainer, where we build your case like a top-tier barrister to absolutely master the Cambridge physics syllabus. Specifically, we're locking in on syllabus code 0625 and the famously tricky topic of transformers. I want you to imagine for a second that you are walking into a high-stakes courtroom. The evidence? That's your grasp of core physical concepts. The jury? Well, that's the Cambridge Examination Board. And the final verdict is your ultimate grade. Now today, we are going to look at some real, heavily scrutinized Cambridge physics past paper questions. And to do this, I want to introduce you to two very typical students we see literally every single year. First up, we have Alex. Take a closely detailed look at Alex's approach here. Alex overloads the exam paper with raw physics facts. We are talking about a massive, rambling paragraph detailing magnetic flux linkage, eddy currents, and Faraday's law, all for a question that simply asks for a straightforward calculation. There's zero critical analysis, it's just a pure brain dump. Then, sitting right next to Alex, is Sam. Sam rushes. Sam is racing the clock. Sam sees the word transformer and immediately scribbles down a mathematical equation, completely ignoring the crucial command word explain, and ends up only providing what's required for a basic state question. You can practically see the examiner's red pen bleeding all over their answers. But don't worry, because today we are going to fix these fatal flaws. We are going to systematically transform those red marks into green check marks.
Okay, let's dive into this massive number right here. 15%. This is absolutely not just a random statistic we pulled out of thin air. Transformers, their intricate construction with a soft iron core, the exact relationship between primary and secondary coils, how step-up and step-down functions operate, the fundamental equation of Vp over Vs equals Np over Ns, and their critical use in high-voltage transmission grids. This entire, massive, interconnected topic accounts for approximately 15% of your total available marks in the 0625 examination. I really want you to think about that. That is literally the difference between two entirely different grade boundaries. It's the difference between an A and a C. So we are going to dissect this 15% today with forensic precision so you leave absolutely nothing on the table when you walk into that exam hall.
All right, let's quickly run through our agenda. This is our examiner's playbook for today. We're tackling the 15% challenge, laying down core transformer principles, building your procedural framework, mastering critical analysis, and finishing up with the top examiner warnings. Let's get straight to it.
Section 1. The 15% challenge. Let's really unpack why this specific topic is such a massive hurdle.
Now, what's really interesting here is that senior examiners constantly highlight a major reoccurring issue. Students notoriously struggle to extract core trends from complex data simply because they lack a systematic, evidence-based approach. Electricity and magnetism, specifically electromagnetic induction applied to transformers, requires you to visualize something you cannot physically see. You're dealing with alternating currents creating alternating magnetic fields. It is highly abstract. Let's go back to our students Alex and Sam. When presented with a complex data table showing voltage inputs, coil turns, and power outputs, Alex panics and tries to memorize the raw numbers. Sam just guesses the relationship based on a gut feeling. Neither of them actually stops to interpret the text. Cambridge physics candidates must demonstrate an absolute mastery of fundamental principles by interpreting these relationships and drawing solid evidence-based conclusions. If the data shows voltage doubling while current halves, you need a systematic approach to immediately recognize that power is being conserved, assuming an ideal transformer, of course. That is the exact conceptual hurdle we are clearing today.
Section 2. Core transformer principles. It's time to build your case. We need to lay down an undeniable theoretical foundation.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, to build an undeniable case for top marks, you really need to understand exactly what the assessment objectives are looking for. You're being tested on your knowledge and understanding, yes, but far more importantly on application and analysis. So let's unlock the exact framework top students use to structure these specific answers. We call it the PEAL framework. Point, evidence, explanation, link. Now, let's play a quick game. Spot the PEAL structure. If an examiner asks you to compare a step-up to a step-down transformer, your point is the fundamental difference. A step-up increases voltage, a step-down decreases it. Your evidence is the physical construction. A step-up has more turns on the secondary coil than the primary.
Your explanation dives deep into the physics. The alternating magnetic field induces a higher electromotive force in the secondary coil due to the greater number of turns cutting the magnetic flux. And finally, your link connects it straight back to the context of the specific question, like its vital role in a national power grid. If you just write down one goes up, one goes down, well, you are acting just like Sam, and you are throwing away easy marks.
Now, the absolute crucial point is mastering this exact equation and deeply understanding the soft iron core construction. Primary voltage divided by secondary voltage equals primary turns divided by secondary turns. It's elegant, it's simple, but why a soft iron core? Guys, this is a classic examiner trap. So many students just write to make the transformer work. No way! Think of the soft iron core as a highly efficient, high-speed bridge for magnetic traffic. Iron is magnetically soft, meaning it easily lets the magnetic field build up, reverse, and collapse without causing a massive traffic jam of wasted thermal energy via hysteresis. It is easily magnetized and demagnetized. This dramatically increases the magnetic flux linkage between the primary and secondary coils, making the transformer incredibly efficient. You have to connect the pure mathematics of the equation to the physical, real-world reality of the device.
Let's look at what separates the top 1% of candidates from the rest. As this breakdown shows, analyzing the advantages of high-voltage transmission targets higher cognitive domains. It moves you way beyond basic memorization. Look at the descriptive level here. This is Alex's trap. Alex writes, "We use high voltage because it's better for power lines." That's purely descriptive. It earns maybe one single mark if the examiner is feeling generous. Now look at the analytical level. A top candidate evaluates the advantage mathematically. By using a step-up transformer to massively increase the transmission voltage, the current is proportionally reduced, assuming constant power using the fundamental equation P equals V times I. Because the power lost as heat in those long transmission cables is calculated by P equals I squared R, dropping the current by a factor of 10 reduces the power loss by a factor of 100. That makes transmission vastly more efficient. Do you see the profound difference there? It's evidence, it's structured reasoning, and it's an undeniable conclusion.
Section 3, the procedural framework. Now we shift gears from what you need to know to exactly how you apply it under immense exam pressure. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at AceTheExams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to AceTheExams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's dive into this standardized sequence. This is the exact procedural framework expected by examiners. It's the physics success blueprint. Let's watch our students rewrite their flawed answers live using this method. Step 1. Identify key elements. Sam decodes the command word calculate and highlights the given values. Step 2. Apply relevant principles. Sam explicitly writes down the formula VP over VS equals NP over NS. Step 3. Execute analysis with clear working. This is where Alex used to just scribble a final number. Now Alex substitutes the numbers into the equation clearly, step by step, right on the dotted lines. Step 4. Verify results. Does a step-down transformer yield a smaller secondary voltage? Yes, it's a quick 10-second sanity check. Step 5. Present in appropriate format. Do not forget your units. Writing just 240 is wrong. Writing 240 volts with a capital V is right. Look at that transformation. That is how you secure full marks.
Listen to me. This is arguably the most vital takeaway of this entire explainer. Applying correct formats and clear annotation proves to the examiner that your analytical process matters just as much as your final answer. Examiners are actively looking for reasons to award you marks. They want to give you points. If you accidentally hit the wrong button on your calculator at the very last second, but your working out in step 3 is perfectly structured, you will still get the method marks. The method is the undeniable evidence of your logical reasoning. It is your ultimate safety net in the exam room. Section 4. Mastering Critical Analysis. All right, let's step into the interactive workshop. We are going to see what truly separates the top-tier candidates from everyone else. Top-scoring candidates elevate their answers by demonstrating sharp, evaluative thinking. Get ready, we're doing 3 rapid-fire challenges. Challenge 1, the data scan. Imagine a complex data table showing transformer efficiency across fluctuating load currents. You have 60 seconds. What's the core trend? Boom. Efficiency peaks, but then it significantly drops as the current gets too high. Why? Because of thermal energy losses, the I squared R heating effect we talked about earlier. Challenge 2, find the flaw. I want you to read this sentence and find the mistake. A step-up transformer increases voltage and power for the national grid. Did you spot the fatal flaw? A transformer absolutely cannot increase power. That explicitly violates the fundamental law of conservation of energy. It increases voltage, which proportionally decreases current, maintaining the same ideal power. Challenge 3. Speed writing. You have 30 seconds to write a PEL paragraph comparing transformers. The secret here? Comparative connectives. Words like whereas or conversely. For example, a step-up transformer increases voltage by having more secondary turns, whereas a step-down transformer decreases voltage by having fewer secondary turns. Using those connectives forces your brain to build a bulletproof comparative case.
Section 5. Top Examiner Warnings. Let's look at the ultimate insider's guide to the pitfalls you absolutely must avoid.
We've thoroughly analyzed the principal examiner reports for the 0625 syllabus, and we've isolated the exact places where candidates hemorrhage marks unnecessarily. These top 3 mistakes prove that contextual accuracy is completely non-negotiable. Mistake 1. Using the wrong approach for the context. If the question specifically details high-voltage transmission over hundreds of kilometers of national grid, do not start talking about the tiny, low-voltage transformer inside your mobile phone charger. Match the physics to the scale of the context. Mistake 2. Forgetting format and presentation. I literally cannot stress this enough. If you leave off the V for volts, the A for amps, or the W for watts, you are just throwing away hard-earned marks. Mistake 3. Providing generic answers. If the exam specifically asks why high voltage is used to transmit electricity to a remote, isolated village, you must state that it minimizes power loss over long distances, ensuring sufficient voltage actually reaches that specific village. Blanketed, memorized answers will get you nowhere. Context is everything.
And this brilliant quote illustrates the ultimate golden rule drawn straight from the chief examiners themselves. You must show your logical reasoning. Your working out is your method mark safety net. We have built our case today. We've examined all the evidence. You now possess the complete physics answering system. You know the 3 rules that guarantee top marks. Number 1, command word decoding. Are you calculating or are you explaining? Number 2, Peel framework application. Point, evidence, explanation, link. And number 3, the time management matrix. Don't spend 6 minutes on a 2-mark question like Alex did. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, ACE Exams at ACEXams_IGCS to excel in your Cambridge examinations. Subscribe right now at ACEXams_IGCS and click that bell. Don't let another exam pass you by. Implementing these precise strategies is exactly what separates average answers from top-tier, outstanding ones. But beyond the stressful environment of the exam room, remember why we actually study this stuff. Transformers aren't just some abstract equation printed on a piece of paper. They are the invisible, pulsing backbone of our entire modern world. They are silently stepping power up and down every second of every day so you can turn on the lights, charge your devices, and stay connected to the global grid. Literally, without them, the modern age goes completely dark. So, as you gear up to absolutely ace this exam, I want you to ask yourself, what other invisible physical forces are shaping the world around you every single day? Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. AC Exams, your Cambridge success starts here.